All right. Good evening, everyone. How you doing? It's Rich Ozer here. John Curry is here with me.
I am here
John,
too. Yep.
and Gerald will be here shortly. He's he's on his way back from the main building. Um, we do have a nice night tonight, and if you've looked outside, you see that the smoke is mostly cleared. Thank goodness. And we're probably going to spend some time looking at planets for a while, and then have a few other objects that we'd like to show you tonight. I'm here at the Chabot Space and Science Center, of course, and sitting in front of our 36-inch research reflecting telescope, who we named Nellie. And I think, well, Gerald will be here shortly. Well, I could put it on Jupiter though, because we already have that in the telescope. So stand by here and I will get you our view of Jupiter.
Is it on Jupiter? Or is it still on the star there?
No, it's on Jupiter.
Okay.
I gotta enable screen sharing. There we go. Share screen. All right. There we go.
There we are.
So I'm going to brighten it up a little bit for Facebook. And what you can see is right here under the cursor is the great red spot. And we have a nice view of that tonight. I'm going to try to magnify it a little bit more here. See if I can. Yeah. You can see it right here under the crosshairs. And we're lucky tonight. The air is much steadier than it has been in our past sessions. So I get to see a little bit more detail. Hey, Gerald. You can unmute yourself and put yourself on video so everybody can see you.
Why would they want to see me?
Well, you said it.
Don't worry, we're all in the dark anyway.
Yeah, that's right. You might want to center this up, and that way I could brighten up the moons.
Okay. All right. Hold on just a second here.
All right, somebody's got Facebook going, so if you can.
Yeah, I just muted it.
All right, thanks. Great. All right, so let's take a look at the moons. I'm going to decrease the magnification here for a bit and bump up the exposure. If I go to like a quarter second, yeah, there we go.
There you go.
Yeah. Oh, that's Ganymede and Io in close, so we can see that.
So that's Ganymede and Io here.
Right.
And
Europa.
Europa, and then Callisto should be out there somewhere.
Might be a little farther out than you can.
Yeah, there it is. It's coming right off the edge of the screen. There it is. Okay, so Callisto is right here under the cursor, and you can see all 4 Galilean moons.
Yeah, my screen is not very bright, so.
Yeah, I'm going to brighten it up a little bit. I'm watching. It comes out different when it gets to Facebook.
There you go.
Yeah, I'm going to go a little bit brighter even. There we go. Okay, so now you can see all 4 moons. And of course, in order to see the moons, the planet gets washed out. So this says something about the human eye, right?
Yeah, because you don't have that problem when you look with your eyes.
And yeah, when you look through a telescope like this through an eyepiece, you see all the detail on Jupiter and you see the moons. When you do it with a camera, you only get one or the other, and that's what high definition means. When you have high definition cameras and high definition displays, it means that they're able to balance the dim and the bright and improve the contrast on each.
Erica wants to know how Ganymede and Io are stacked on top of each other. They're not really. Ganymede is actually moving around the planet toward the back, so Io is closer to us than Ganymede is at this point, and that they just happen to look like they're close together. They're not really.
Yep. That's one of the, it's one of the dilemmas that astronomers always have is, we get a wonderful two-dimensional image of the sky looking through telescopes and looking through our eye. Judging distance is a real trick. And you either have to know the orbital elements of what you're looking at, or you have to do all kinds of other tricks to figure out what's closer and what's farther away.
Yeah, the actual order in terms of closest to farthest, Io is the closest
Closest to Jupiter.
to Jupiter.
Yes.
Yeah. And then Europa is the next closest. Ganymede is the next one. And then Callisto is the farthest of the four.
Right.
They are not all the same size. Ganymede is the biggest moon of Jupiter. It's also the biggest moon in our solar system. Io is, let's see, Callisto is the next biggest. Io is the third biggest, and Europa is the smallest of the three. And one of the interesting things about them is the moons are in what we call mean motion resonance. Io takes 1.8 days to orbit around Jupiter, and Europa takes 3.6 days. 3.6 days is exactly twice as long as Io, so it's in what we call a 2-1 resonance, because Io goes around Jupiter twice for every one orbit of Europa. And then Ganymede's orbit is exactly twice as long as Europa's orbit. So same deal. Europa goes around twice for every one orbit of Ganymede. So we call those mean motion resonances, and it's actually pretty common. We see mean motion resonances in a number of places. We're going to look at Pluto and Neptune a little bit later on here, and they are actually in a mean motion resonance. Neptune goes around 3 times for every 2 times for Pluto. So pretty common occurrence in the solar system.
And that's all caused by gravitational tugging over a long, long period of time.
Right.
So let me go ahead and change the exposure now so we can take a look again at the detail on the planet.
Yeah.
I'm going to go to 30th of a second.
So Jupiter is
there we go.
11.2 times the diameter of the Earth. So it's 88,000 miles across. We don't have great viewing conditions tonight, so we can't see the banding on it very well.
Well, let me.
We did see the red spot before, so.
Yeah, we were still seeing the red spot here.
Again.
Hold on. Yeah, I'm playing around with the focus for a sec. Let me see if I could improve it here. Oh, that made it softer.
Yeah.
Go the other way.
We want to sharpen it to crystal clarity.
Yes, like we're in orbit around it.
Yeah, it's getting a little bit better. I've seen hints of it. Yeah, you're going soft again. Yeah, now you're way too soft.
Yeah. This goes in very large steps.
Yeah. So while he's playing with that, Jupiter is a gas giant. So it's basically a big ball of gas with maybe a very small solid core at its center. Gas is mostly hydrogen, but there are other gases in the atmosphere as well, like methane, carbon dioxide, and so forth. Jupiter's atmosphere has high and low pressure areas, just like on Earth. But because of Jupiter's rapid rotation, the highs and lows get wrapped around the planet. Jupiter, even though it's 11.2 times the diameter of the Earth, its day is only 9 hours and 50 minutes long. So it takes 9 hours and 50 minutes to make one complete rotation. And as a result, things are moving really fast, especially at the equator. And that just wraps those highs and lows all the way around the planet. And in general, when you see dark bands, those are the low pressure areas, and the light bands are the high pressure areas. But if you were to zoom in, if you will, you would actually see a lot of eddies and turbulence within the atmosphere. It's very chaotic in the atmosphere.
I'm going to try something here if you don't mind for a second. I
Okay.
want to try changing a video setting here to see whether I can improve this. I hit share screen again. Yeah, that actually is a little bit better. Okay, so now you could see the red spot better, I think.
Yeah,
Right.
point
See
it
that?
out there. Yeah, point it
Yeah,
out.
I'm going to point it out
Right.
right here,
There you go.
right there, and I'm moving my cursor now, and you'll see the red. What I did here, Gerald, is when you share a screen in Zoom, there's a
Yeah.
checkbox that says optimized for video clip.
Oh,
And I figured, this is kind of like a video clip. And so it seems to smooth it out. Yeah, that's much
yeah,
better.
that
Look
looks
at that.
better. Yeah, yeah. All right. So right now we have a spacecraft orbiting around Jupiter. It's called Juno, and it's been taking some pretty spectacular images of Jupiter. And one thing they've been doing is they've been sharing those images online and encouraging amateur photographers to use the images to enhance and show even more detail. And the result has been some really spectacular images that some amateurs have been putting together where they combine images from Juno and just create these really high detail images, close up images of Jupiter's atmosphere. And it's been pretty amazing. So if you're an amateur, photographer, and you want to play around with Juno's images, just look up Juno, Juno. It's a spacecraft orbiting around Jupiter. I believe. Yeah, I'm not sure. I'm not sure. I think it's John Hopkins, but I'm not 100% sure that that's managing the spacecraft. All right.
That's nice.
Yeah. Well, you want to go on to Saturn?
Let's do it.
All right. Well, Saturn is actually not too far away from Jupiter, in terms of its position on the sky.
Yeah.
They're actually very far away. They're more than 400 million miles apart from each other, but they're very close to each other in terms of our line of sight on the sky. So I'm going to slew on over to Saturn, which will be a fairly short slew here. And over the next several months, Jupiter and Saturn are going to get closer and closer together. And the reason for that is that Jupiter orbits the sun faster than Saturn. And as a result, Jupiter laps Saturn periodically. And that's what's going to happen here. That's a pretty good view there. Let me get it centered up for you. That's not too bad, actually.
Get that brighter. Here we go. All right.
I always push the wrong button when I'm adjusting it.
Well, there's so many buttons.
Yeah. Yeah.
All right, not bad.
Yeah, not too bad. We can get little hints of the Cassini division. There's actually a break in the rings. It's about a third of the way in from the outside edge, and it's called the Cassini division. And if you were to look close up to the rings, you would see that they're actually composed of hundreds of rings, sort of mini rings. And it's almost all ice with a little bit of dust. And those ice particles are not very big, mostly fist size or so. A few maybe the size of a small desk or something like that. And the ring thickness is very thin. It's only 10 to 20 meters thick in most places. There are a few places where it gets a little bit thicker because there are some very small moons embedded in the rings. So they can disrupt the rings a little bit and make them look thicker. Now, one thing I want to call your attention to, if you look carefully above the planet, just to the left, you'll see that the ring sort of breaks before it gets to the planet.
Right here he's talking about.
Right. And the reason for that is the sun is not directly behind us with respect to the planet. The sun is actually off to one side a little bit, and it's casting a shadow onto the rings. So that little dark spot is actually the shadow of the planet itself on the rings, sort of behind the planet. It's because the sun is slightly off center.
Okay, so the sun you could think of as being right here where my cursor is.
Yeah, more
Right.
like a little bit closer in, but you know,
Like that, and
behind
then
us.
the light rays are hitting this way, and the planet is casting a shadow over
You got
here.
it. Yeah, that's it. Yeah.
All right.
Now we never see the dark side of Saturn because Saturn is farther away from the sun, actually quite a bit farther away from the sun than the Earth. So no matter where we are in our orbit, we're always looking at the lit side of Saturn, but not straight on. Sometimes we're a little off one side or the other, and that's when we get that shadow that you see there.
That's pretty neat.
Yeah, yeah,
It's very distinct tonight.
yeah. Yeah, we had really excellent viewing conditions this past Monday night. And so we were able to see all of this detail extremely well. It was really fascinating. You could also see some banding on the planet itself. Now, people sometimes ask us, well, why is it white? And if you look carefully, it's actually not white. It's kind of a creamy tan color. And if you were to come up here and look through our telescope with your eye, where we've zoomed in a little bit more, you would see that there's some yellows in there as well. But they're all very pale colors. There's not a lot of color on Saturn. But you may, if you're searching on the internet or something like that, you may see photographs of Saturn where it looks much more colorful. And that is not a true color image. That's a false color image or an enhanced image where they've enhanced it to sort of bring out some of the finer details. So either deliberately making parts of it the wrong color or enhancing the very slight contrast between one shade of, tan and another shade of tan to make details come out better. But what you're seeing right now is the natural color of Saturn. Now, Saturn has quite a few moons. In fact, I was reading this morning, we're up to, I think, 82 moons around Saturn. Although a couple of them are sort of, less than a kilometer in diameter, so they're not very big. And there's some debate about whether anything smaller than a kilometer should be considered a moon. So you've cranked it up, and we've got that fake moon up and to the left.
Yeah, this is my named hot pixel. But I think, I don't really see anything else.
We're trying to see Titan. Titan is the biggest moon of Saturn. It's actually bigger than our moon, and it's one of the few moons in the solar system that has an appreciable atmosphere.
I don't have any sighting here of
yeah.
Titan, so.
I'm gonna move things back and forth if you don't mind.
Possible. Go ahead. It's possible it's off to one side, right?
It's possible. We'll move a little bit back and forth. Shouldn't be too far outside, though. Yeah, I'm not seeing anything here. So
I'm not either. Yeah. Oh well.
Not sure why, because we normally can see it pretty well.
Bring it all the way to the left.
All the way to the left?
Yeah.
Okay.
Yep.
Oop,
all right.
Went too far there.
Yeah. Bye. All right. Well, it was worth a try.
All right. Okay, so we've looked at the two bright planets. These are planets you can see with your naked eye. If you go outside right now, assuming you're not in fog or smoke.
Well, wait a second. Everybody who's looking on a somewhat larger screen, You can really see that Cassini division popping out right now. Right
Oh
there.
yeah, 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 yeah.
Right,
So we
I'll
get
move my
moments
cursor.
of clarity.
Yep.
So
All right,
anyway,
anyway, you were saying.
yeah, if you go outside right now and you look up almost straight south, you'll see two bright objects, one quite a bit brighter than the other. The really bright one is Jupiter, and then to the left of it is Saturn. And if you hold your arm at arm's length and hold up two fingers, the spacing between the two is just about the width of two fingers held at arm's length. That's one of the techniques we use to kind of gauge, the separation between objects is just extend your hand and use your fingers. So anyway, those are the two planets that we can see right now. If we were to stay up until about midnight, we would be able to see Mars. Mars is starting to get up above the horizon right around 9:30 or so tonight, but it'll be so low we won't be able to see it until much later. But over the next several weeks, Mars will get higher and higher each night. And starting in late October, we should be able to view it at this time of night from here at Chabot. So that's something to look forward to.
Mhm.
And Jupiter and Saturn will stay in the sky for quite a while. But in December, because Jupiter is moving faster than Saturn, they will get closer and closer together in our line of sight. And in December, late December, they will be so close together that we'll be able to see both of them in the same field of view with our telescope. Unfortunately, it's going to be just after sunset when we'll be able to see it, and so it'll be a little too late by the time we get to our virtual program. But we're going to take edges of it and make sure everybody gets a chance to see that.
And that'll only be for one day.
Right.
Very close.
Right. Now, in addition to the planets that we can see, we wanted to show you a couple of planets that are actually pretty hard to see. And one of them right now is halfway in between Jupiter and Saturn. And that's that great planet, actually the dwarf planet, Pluto. So what I'm going to do right now, I'm going to make sure we're precisely synchronized.
Now we're going to have to take longer
and
exposure for that.
Yeah, we're going to have to do a fairly long exposure, and you're going to see Pluto, but you're going to be really disappointed.
Hopefully we're going to see Pluto.
Well,
hopefully we can disappoint you.
Yes, it will be in the field of view, but you're going to see why it was such a difficult thing to see. And then I'm going to show you the actual discovery images of Pluto, and I'll talk a little bit about that. So I'm going to slew to Pluto, and then Richard's going to take a long exposure photograph so we can see lots of stars.
Okay, I think
we are there.
It makes sense to take
I would go at least 30 seconds.
Like 30 seconds,
Yeah.
And I'm gonna we'll try it at ISO 1600 and see what happens. Okay. So cue the Jeopardy theme here.
Now, we have a way of rating the brightness of stars and planets. Astronomers use something we call the magnitude system. And it's a kind of an odd system. Each magnitude represents a logarithmic decrease in brightness. So magnitude 1 is actually dimmer than magnitude 0. Magnitude 2 is dimmer than magnitude 1, and so forth. So the bigger the number, the dimmer the object is. Not only that, but each whole number magnitude increment represents a difference in brightness of 2.5 times. So this object that we're looking at, Pluto, right now is at magnitude 14. Now, just to put that in perspective, if you found yourself a really dark sky location up on the top of a mountain far away from city lights, the dimmest stars you could see would be around magnitude 6. So Pluto is 8 magnitudes dimmer. So if you want to know what that is, take the number 2.512 and raise it to the 8th power, and that's how much dimmer it is. So anyway.
That all being said, do you have the star field?
Well, I see the star field, and if our pointing is correct, then right smack in the center is Pluto.
That one?
That one right there.
Okay, does everybody see where my cursor is? All right, now I'm going to move it. 1, 2, 3. There's Pluto.
Pluto.
Right there. Whoops, I overshot it. Right there.
Yeah, what a disappointment.
And there. You know, this is like the best view of Pluto I've ever had. So I'm not at all disappointed.
Yeah. So Pluto takes 248 years to make one orbit around the Earth. Pluto was discovered in 1930 by Clyde Tombaugh. So that was only 90 years ago. So Pluto hasn't even completed one full orbit around the sun. I think I said the Earth a while ago. Yeah. 248 years to orbit around the sun. And in 90 years, it has not even completed 1/2 of an orbit around the sun. So Pluto moves really slow. So if we came back and looked at Pluto again in an hour, it would look like it's in the exact same position. But if we waited several days and then took a picture again, Pluto would be in a different position. And that was the technique that Clyde Tombaugh used to find Pluto. Now, I want to, if we can, if I can share my screen. I don't know if
all right. You have rights. I might have to stop first. Hold on.
Yeah, it says, all right, let's try that one more time. Where is it? There we go.
In the meantime, Ginger has asked, what is the bright star on the left? All of these stars in the field are very, very dim stars.
They're all nameless.
Okay,
they just have catalog numbers.
Okay, so we zoomed in on Pluto here. Can you see it?
No, all we see is your directory. You haven't shared the image. You've shared your file system.
Okay, it says I'm sharing here, so.
Yeah, you guys just share the right thing.
All right, hang on here.
You can share your whole desktop, and that'll work.
Okay. Why is this not working? I'm going to close that, and I'm going to close that.
Okay, hit share.
Yeah, hit share.
Go ahead and share up there. Share that one, and then just move the windows around. You could.
What if I just?
You could do an Alt tab.
Open this.
Yeah, there you go.
There we go. All right. Now can we see it?
Yep.
All right.
Yes.
All right. Sorry about that.
It's all right.
I'm not the most computer literate individual. Anyway, so this is a close-up image. This was actually taken by the New Horizons spacecraft when it flew by Pluto back in 2015. It's been that long ago. And if you want to know why it's called Pluto, just look at this feature right here. Here's Pluto's head. Here's his neck. Here's his snout. Here's his nose. There's Pluto, right? Okay. So let's see. I got to get this out of the way here so I can advance my image.
Well, one of our other astronomers has answered the question. The star to the left of Pluto was TYC 6889-1241-1.
Oh,
and there'll be a test at the end of the night.
So I'm showing now an image of the actual telescope that Clyde Tombaugh used. This is at the Lowell Observatory in Flagstaff, Arizona, and that's my daughter standing next to it. And you see that kind of rectangular structure on the back end of the telescope. He would put these big glass plate emulsion plates in that frame, and then take exposures, and he would point it at the same part of the sky every night, and then he'd go and develop them. And then after he developed them, he had to look at them. The device he used to look at them, well, I jumped the gun here. Okay, these are two of the image plates that he got. These are the discovery images of Pluto. And you see one was taken on the 23rd of January, 1930. And then the second one was taken on the 29th of January, 1930. So 6 days apart. And you see all the same stars in the field of view, but that little dot there has moved over to there in this image. So it's gone from here to there in that 6 day period. And the way you recognize this is you take these two images and you put them on a device called a comparator, blink comparator. And this is the one he actually used. And what you do is you put them on there and you very carefully line up the images. When you look through the center eyepiece right here, you start out, you see both images superimposed on each other, and you have to line them up so all the stars are in exactly the same position in the image. And then you blink back and forth between them. And when you do that, you see the planet Pluto moving back and forth between these two positions. And that's how they discovered Pluto. So at the time, they thought it was a much bigger planet than it turned out to be. So anyway, that's how we discovered Pluto. I'm going to stop my share now.
Oh, I gotta mention something real quick. So folks, every once in a while, you're going to be seeing something pop up talking about a place you could stream Chabot live telescope viewing that has an unknown to us URL, watchstreamslive.com. And we've seen a lot of this in the last couple of weeks. There's some kind of phishing scam going on. So please
don't go there.
Only go to Chabot Space and Science Center Facebook page and Chabot Space and Science Center website, and any of that other stuff, please ignore, because we don't want anybody to fall for any scams.
All right. So anyway, you had a chance to see Pluto. If you want to share your screen again, Rich.
Oh, sure. Hold on. Yeah, that's pretty neat. This is, I'm actually going to show this photograph tomorrow night to some other people.
So there it is, we think.
Yeah. There it is, we think. Hey, prove us wrong.
Yeah, exactly.
Yeah, right.
Who's going to argue?
Yeah.
Okay, so we have another planet to look at, and it's quite a bit farther over in the sky. So I'm going to slew there, but I'm going to do it in steps so we stay synchronized.
This might be visible through live view.
Yeah,
Maybe.
yes, it should be. Yeah. All right, so I'm going to go here first. So we're going to go to a star and make sure we are synchronized.
Yep, there we go. That's the star.
How are we looking as far as
it's not? It can improve the centering here. There you go.
Okay, hang on. Wrong direction every time.
Hey, it's a 50-50 proposition.
Yeah, most of the propositions I did in my youth were less than 50-50. Bad.
Yeah.
Bad.
I've learned not to respond to those types of things. It just gets me into worse trouble.
Okay, so we're synchronized on that. Let's head on over to the planet Neptune. All right. Here we go. Now, it's not going to be really big, but if we're lucky,
No,
we
but
might
it has a
actually
nice color. Yeah, it
might
has a
see
nice
some color
as
to
you
it.
see. Yeah, if we're lucky. Okay,
right.
I'm not seeing anything yet, so we may have to take an exposure. So let's.
Yeah.
Let me just
Yeah,
make
this is
sure
at
that.
magnitude 7.8, so it's
Yeah,
pretty
let me go for an exposure here and go for um,
Oh, there
15
it is, right
seconds.
next to Pluto.
Yeah, right. All right, Jeopardy music.
Yeah.
15 seconds.
So while we're waiting for that, let me tell you a little bit about Neptune. Neptune is the uh, um, by depending on how you want to count it, it's the eighth planet from the sun. It is a giant planet. It's just under 4 times the diameter of the Earth, so it's not a really
There we
big
go.
giant. Hey, there it is.
Right up here.
I can even see a moon. I think
Yeah.
I see Nereid, right? Or is that Triton? Triton,
I
right?
think it's Triton.
Yeah, yeah.
All right. Very nice.
Me,
And Neptune is a mere 2.7 billion miles away.
That's a quick car ride.
yeah, just for reference, if you consider the distance between the Earth and the Sun, the average distance is just under 93 million miles. We call that an astronomical unit. And the distance to Neptune from the Sun is 39 astronomical units. So it's 39 times farther from the Sun than the Earth is.
Sharpen it up a little bit so you can see
39
that
or
better.
29, Gerald?
39 times farther. Oh, I'm sorry. I'm looking at the wrong planet. I'm thinking of Pluto. 30 times. 30 times farther from the sun than the Earth. So it's 29 astronomical units away from the Earth right now.
Right.
Sorry about that.
I hope you folks on Facebook can see the moon there, Triton. So I'm trying to brighten it up. Yeah, there we go. That's probably a good idea for some of you with smaller screens.
Yeah, there you go.
I'm going to try to center it. I'm going to hope I go in the right direction, but given my
and then we'll take another shot.
My shot at propositions, I'm going to.
Yeah, here we go again.
Yeah, let's not go back there.
All right, so do another shot and let's see what happens.
All right, here we go.
I either went the right way or the wrong way. See, when I'm looking through the eyepiece, I just use the step on the ball.
Right. Oh, good.
Technique.
Somebody responded that the Facebook folks could see it. That's great. All right. Let's see if it's more centered this time.
Either that or it'll be out of
or
the frame.
it's the off. It barely moved at all.
Oh, I went the right direction.
But you did go the right direction. You just need to do more of it.
Okay. All right, you can try it again.
Okay.
Yeah, but Triton is pretty bright there.
Yeah. So Triton is it similar to Titan in that it's a methane atmosphere?
I believe so. Yeah, and it's got a nitrogen atmosphere, and I think it's the one that has the nitrogen volcanoes on it.
Oh, nitrogen rather than methane, then, huh? Okay, interesting. All right, that's not bad. Yeah, you don't need to correct it any further.
Yeah. Okay. So you got lucky. You got to see 4 planets tonight.
Yeah, and several moons.
Pretty good. Yeah. So just the one other thing I wanted to say, I think I already told you its diameter is about almost 4 times the diameter of the Earth. And like I said, it's 30 times the distance of the Earth to the sun. All right.
Yeah, that's great.
Okay. Where would you like to go next? I was thinking maybe M15 and then M33.
Yeah, we got it. Well, we always have to stop at M15.
All right.
You know,
okay.
We know how much you like M15. And then we'll go take a look at those planetaries and Cygnus maybe afterward.
Okay. All right. Well, we'll go to M15 and then I'll let you decide where you want to go next.
Okay.
All right. So we'll do my one of my favorite objects. M15 is a globular star cluster. It's 33,600 light years away. It has somewhere around 450 to 500,000 stars in it. All right, we should be there.
All right, let me shoot. I'm going to use the same exposure. Should be pretty good for
Yep.
this object. Oh, you're a little bit off.
A little bit.
Yeah.
A lot.
Well,
Okay.
just go back the other way that you
Okay.
that you did
Yeah.
with Neptune, but the other way.
All right. Try it again. Let's see. Right is west, right? I was still moving it. Sorry.
No, that's all right.
In the meantime, Jasper asked, Uranus is not visible, and that's correct. It's a way too far over
Yeah.
the horizon for us to get it right now.
Need more. And everything is doubled here. So you notice how that star up here.
Yeah, that's because I was.
It's because we were moving it while we were shooting.
Yeah. Okay, go ahead.
All right.
So anyway, this is a globular star cluster. There are at least 150 globular star clusters in the Milky Way galaxy. And most of them are in what we call the halo of the galaxy. So if you were outside of the Milky Way looking at it, it would look like a
very good.
traditional spiral galaxy. I'm going to go a little bit farther here. It looks like a flat disk with spiral arms in it. It's got a central bulge. And that's where most of the stars are. But surrounding that flat disk is a kind of a spherical shell, if you will. It's a very diffuse shell and very few stars in it. And it's in that halo region, that's the region we call the halo. That's where you find the globular star clusters. And there's about roughly 150, 160 of them orbiting around the galaxy. It doesn't seem to have moved.
Yeah, it just takes a little time.
Oh, there you go. There you go. There you go.
Yeah.
All right. So now you see it.
It's nice.
And most of these globular star clusters are extremely old. They are among the first stars to have formed when our galaxy was forming more than 11 billion years ago. So they are very old stars. When the clusters first formed, there were stars that crossed the whole range of masses. But massive stars don't live very long. A star that's maybe 10 times the mass of our sun will live much less than 1 billion years, whereas our sun is already 4.5 billion years old. So what has happened is all the really massive stars in the globular star cluster have actually gone away. They've died. They either blew up as a supernova or they died became white dwarfs and planetary nebulas and so on. And what remains are all of the lower mass stars. Low mass stars live a long time. So in the cluster are a lot of low mass stars. The stars are orbiting around the cluster, and most of them are in highly elliptical orbits that go in close to the center of the cluster, and then they swing out and they go very far out towards the periphery of the cluster, and then they swing around and come back in. So these are highly elliptical orbits. When they're close in to the center, they're moving very rapidly, and when they're out far away, they're moving very slowly. Now, there are a lot of stars that are actually concentrated near the center of this cluster, much more so than most globular star clusters. So we call this a core collapse globular star cluster. And when we measure the density of the central part of the cluster, it's so dense that there is a strong indication that there is an intermediate mass black hole at the center of the cluster. So we can't see it, but all these stars that are very close into the center of the cluster are orbiting around that intermediate black hole. Now, we don't know 100%, but there's very strong indication that that black hole exists at the center of this globular star cluster.
Has there ever been any X-ray evidence?
I'm not sure off the top of my head. The way we measure mass is by looking at the stars that are orbiting around the cluster, especially the ones that are a little bit farther away from the center, and measuring the velocity that they are moving through space. And you do that spectroscopically using that blue shift and red shift concept. You can measure the velocity. And the velocity is a function of the total mass of the cluster. And so once you know the velocity of the star, you can measure its mass of the whole cluster. And then we make a big assumption. The assumption is that the mass of our sun is the average mass of all stars. So you take the mass of the cluster, divide it by the mass of our sun, and that gives you a big number, 450,000, give or take. And so we say that's how many stars there are. Likely that's not a really accurate number, but it's close enough for government work.
Or astronomical work.
Or astronomical.
How in the world did Lisa get in our image here?
Is she?
She has somehow or other gotten into our Facebook thing.
I don't see Lisa.
Oh, really?
Yeah.
I do.
Let me see. Oh. Yeah, I think you're looking at the wrong Facebook video.
That's interesting because I was looking at the right one.
Yeah, it looks okay from my perspective.
Okay,
here, so.
well,
Yeah.
whatever. I don't know what happened there.
I mean, yeah, that is Lisa, but she's not here. I mean, I'm looking around the room here.
Lisa?
Yeah.
Oh, well, I don't know what the heck happened there. Well,
if you really want to confuse Gerald, you just have to use a computer.
Really?
He
Not
never
my
met one that he didn't hate.
Yeah, that's right. Oh, that's too funny.
Okay, well, where else would you like to go, Richard?
Why don't I think going to M33 is a really great idea because it's another dramatic object. So let's start with that, and then the others are more marginal, and we may or may not have luck. But let's go for the biggest bang for the buck here, and
all right,
go for the big galaxy.
I'm going to head first over to Alpha Rats, or as some people say, Alpha Rats, and
okay, I'm going to put it back on live view.
All right.
Alpha Rats.
Yeah. Most of us say Alpha Rats, but I was listening to a program the other day on the radio, and the guy kept calling it Alpha Rats. Don't ask me why.
There's no Y in there or anything like that.
Yeah,
I don't know why he would come up with that.
All right. Are we on live view?
We are on live view, and I am not seeing it.
Well, that ain't good.
Let's
see. I went east, right? So
hold
let me
on
go.
for a moment. Yeah, it's not in the field, so.
Oh, it's looking in more or less the right direction from where I'm looking here.
Well, that's why we do this. So maybe center it up in the finder.
And Mars is too low yet.
We may have to center it in the finder.
No, I don't even see it in the field.
Okay. All right. Well, bear with us, folks. I'm going to get offline here for a second.
Alpha Rats.
Well, maybe you offended it by calling it Alfie rats.
And if
Did
you
you get
call it diddly squat, it'll really get upset.
Oh, I don't see it yet. No. Let me check the camera field again. I still don't see it in the camera field of view.
There you go. That's coming into view. Stop. Stop moving. All right,
Oh yeah, there it
it's
is.
in the view.
All right. Great. So, alpha rats. Let's go ahead and sync on that. I'm going to move the ladder out of the way.
Okay.
All right. All right.
So when we do this kind of stuff, you may think, oh, what a bunch of amateurs. But actually, this is real stuff. This is what we go through when we're doing astronomy. Isn't it?
Yeah, and you got to realize our field of view through a telescope like this is like the size of a pea.
Yeah, very small. Imagine holding a soda straw up at arm's length and looking through it. That's about how much of the sky we're seeing right now.
All right,
So,
I'm going to put up the crosshairs in case you want to get it right.
all right. Okay, we are on our way, I think.
I'm not seeing it move. Yeah, wrong way.
Yep.
There we go. Yeah, what we're going to do is get this dead center, so when we slew to M33, there's a good likelihood it'll be in the center.
Or close.
Or close. And a little bit down there. It's probably good enough. Yeah, M33 is pretty big, so that'll do it.
He wants it perfect.
Yeah, I'll bet all the paintings in his house are straight.
Right.
Found me out. Okay, here we go.
Ready?
Okay,
I'm sure we will see nothing in live view. But,
yeah, this is
it's a dim
magnitude 8, I think.
Yeah, it's a dim galaxy that is very close to us. It's like in Andromeda range almost, and it's huge, but it's much dimmer.
And it's coming our way. It's 3.1 million light years away, so it's a little bit farther than Andromeda.
I'm going to go for 30 seconds on this. Oops. And it's F16.
And that's not it. That's
no, that's not
still
it.
our globular cluster.
Yeah.
That's the previous image.
Every time I go back to this screen, you see what we were doing 10 minutes ago.
Yeah. So M33 is a spiral galaxy similar to our Milky Way galaxy. It's 3.1 million light years away, and it's moving toward us. It's approaching us at about 179 kilometers per second. So if you hang around long enough, you might be able to see with your naked eye.
Really long enough. Really long time.
All right, it is. We are actually there. It's very
there. Yeah.
Let me see what I can do here. It's really barely.
Yeah.
I'm gonna have to go. Let me go for longer exposure. you know,
What ISO are you at?
1600. I could
Yeah.
bump that up too, but let me go to 60 seconds. Let me go to 3200.
So one of the problems we have when we're imaging galaxies is you'll see, if you look in a star chart, you'll see a magnitude figure like magnitude 7. But that magnitude represents the surface brightness of the whole thing.
Yep.
So if you have a magnitude 7 star, all of that brightness is concentrated in one little point of light. But a magnitude 7 galaxy, that brightness is spread over the entire galaxy, which is going to cover, a fairly large part of your field of view. So, the same brightness object is not necessarily going to look the same in your image. So that's why we're doing this longer image here, 60-second image, and hopefully we'll be able to see a little bit of detail. I can see some of it, but
I can see some of it. I see some of the
Yeah.
hydrogen regions, but
Yeah.
it's like it's hard to point them out. And I'm sure
It-
that on Facebook you're not
it
seeing them.
will be kind of tilted a little bit. We're at a little bit of an angle to it. And the answer is
Okay, this might be a little bit better. Hold on for a sec here.
still pretty faint.
Let me try something.
So one of the things we can do with images is sort of adjust different
There we go.
parts of the sky. Yeah, they got a little bit of it in there.
Yeah, there we go.
Oh,
Yeah.
Okay, so the part,
well-
what you could see here is if you look in this region here, you're seeing the core right here, and you're seeing some amount of the spiral arms
Yeah.
coming here. And it is actually a very, very large galaxy, and it goes out to over here as well. And this is one of the hydrogen alpha regions, as is over here. All these star-forming regions throughout M33. It's kind of famous for being able to observe those. But that's probably about as good as we're going to get, I think.
Yeah. Unless you want to sit here for a couple hours.
Yeah, I mean, we could take a 2-minute shot and see what we get. But
in the meantime, I can show a starry night image of it if you'd like to see
Oh, there you go.
yeah,
what it looks
yeah,
like.
yeah. Why don't you do that?
Starry Night or a Hubble Space Telescope or
Yeah.
something like that.
I need to.
It'll look a lot better than this.
Yeah, I need to. How do I? Let's see. I gotta share my desktop.
Yeah.
Hopefully-
Zooming in doesn't help.
Hopefully you're better at it than I am, John.
Okay, I'm going to stop
Actually, I
sharing, and you
Done
can
this
share
a bit.
now.
Okay.
You see the back end of the telescope above Richard's head there.
Yeah, there we go.
All right.
That's good.
Yeah. So you see how some of the spiral arms kind of extend out to one side. And that's what Richard was trying to point out to you, what he was describing as the H alpha regions. H alpha just refers to hydrogens.
and the
red wave.
rotation on this one. If you look to the lower right, there's a bright star, and then you see kind of a fuzzy bright area under it. That was at the 1 o'clock position in the image we took from Nellie. So that first hydrogen alpha region I pointed out was that section. So this is rotated about, I don't know, 40 degrees clockwise from what we had.
And the galaxy even has a big label right in the middle of it. M3.
Yeah, that's how they knew what it was.
Right.
Yeah, that's right.
So they decided it.
It made it very easy to discover because it said M33 right in the middle.
Yeah, we're so funny.
It's like when you look for the arrows, that blink comparator that you showed
right,
earlier.
right.
It's like they would have never found Pluto if there weren't arrows pointing to it.
All right. Well,
Yeah.
we got a couple other objects we want to look at.
Yeah, we're going to try some other challenging stuff. So we had a couple planetaries. The top one on that list is the brighter and easier of the two.
Okay, I'll go to that one first.
So if that doesn't work out, we may not even try the second one.
What constellation is it in?
This is in Cygnus.
Oh, all right. Okay. Get back toward Cygnus here. Okay, I'm going to slew to a magnitude 2.5 star, and we'll set that to synchronize.
All right.
So our telescope is computer controlled. So all we have to do is go to the computer and give it a set of coordinates or select an object from a list, and it goes there.
Or reasonably close.
Yeah,
there it is in the lower right. And,
yeah, all right. So we need to go down, and we need to go west, right?
Yep. Okay, that looks good.
All right. Sunk on that. All right. So let me call this up.
Now, what we're going to try to take a look at is Planetary Nebula in the constellation Cygnus. And it's only known by its NGC number, which is 6826. Is that what I have down there?
6826.
Yeah, 6826. And it's a small one. It's reasonably close. It's close. It's 2,000 light years away. But as galactic objects goes, that's in the neighborhood.
It's sometimes known as the Blinking Planetary.
And there's a reason it's called that. First we'll see if we can see it, and then we'll. Okay, let me go ahead and shoot it with a I'm going to try a 30-second image and see what we get.
It's a magnitude 10 object.
And let me go to 40 seconds.
But it should be more concentrated than the.
Okay, so while that's shooting, I'll tell you why it's called the Blinking Planetary. So this is one of these objects which has got a very different brightness in the center than it does at the edge, and different parts of your eye are sensitive to different parts of the planetary nebula. So when you're staring straight at it, you don't see the fuzzy ring around the central star. And when you use averted vision, looking to the left or to the right, suddenly that pops into view. And that's because different parts of your eye are sensitive to different types of light. When you're looking straight on to something, it's more sensitive to color. When you're looking offset, it's more sensitive to black and white and dim objects. So it got called the Blinking Planetary because people would look at it and they'd move their eye around and it would look like parts of the nebula would blink on and off. Oh, that's excellent. Look at that.
Yeah.
Well, there you go.
Now, Richard, you used the term averted vision. Why don't you explain what averted vision is?
Okay, so if you've got two kinds of cells in your eye. You've got rods or structures. You've got rods and you've got cones. And the cones are sensitive to color, particularly blue and green light. And rods are sensitive to black and white. And they are what contribute most to your night vision. And when you're looking straight on to something, you're using your cones. When you when you move your eye, so you're looking askance at it, then you're using your rods. And in a dim environment, it's actually the edges of your vision, your peripheral vision, that's more sensitive than the center. But you have to learn how to pay attention to what's on the periphery of your field before you can master the art of using averted vision. So it's a little mental trick as well as a physical trick.
So what you would do, rather than looking directly at this object through the eyepiece of the telescope, you would look slightly off to one side, and that exposes the light to more of the cone or the rods rather than the cones, and then it becomes a little bit brighter. And like Richard says, it takes some skill learning to look that way and still perceive detail, but it actually works out pretty well.
Yeah, your eye keeps wanting to look back directly at the object.
Right.
Yeah.
And that confuses
Kathy said she uses averted imagination.
Yes.
Yeah.
That really works well.
Yeah. That's always works.
Yeah, astronomers use a lot of averted vision, but we use even more averted imagination.
Yeah. This is a much better picture than I expected.
Yeah.
I've got to say. So again, this is a planetary nebula called NGC 6826, and a planetary nebula has nothing to do with the planet, right? But it was when these things were first discovered, people thought they kind of looked like, they were looking at, Uranus and Neptune, and then they'd go to something like this and say, oh, maybe it's a planet. But it's not. What it is a star that has it's ending its life cycle. What you see here is a white dwarf star in the very center of that teal dot, and the material around it is gas that has been shed by that star as it cools off. And the star itself is what's known as a white dwarf star. And this is what's going to happen to our sun at some point.
Now, the reason for the teal color, this star, as it got towards the end of its life, it began to fuse and produce oxygen in the star, and that was then blown out when the star became a red giant. And most of the gas that was thrown off the star when it was a red giant was hydrogen gas, but some of it was oxygen. Actually, a small percentage was oxygen. When the star became a white dwarfs are very small, very compact, very dense objects using what's called degenerate matter. And white dwarfs emit a lot of ultraviolet radiation. The ultraviolet radiation goes out and it hits the gas that was expelled by the star when it was still a red giant. And it causes the gas to glow. It ionizes the gas, causing it to glow. And the oxygen in the gas glows this very, very bright turquoise or teal color that you see. Now, that makes you think that it's mostly oxygen, but actually that's not the case. Most of the gas surrounding the white dwarf is hydrogen gas. But hydrogen gas, when it's hit by that ultraviolet radiation, it glows in a very deep, faint, reddish color. And we would have to use filters to really see that very well. And it would turn out that the hydrogen gas takes up a much larger part of this image. It's just you can't see it because it's faint and in this dark red part of the spectrum where your eye doesn't perceive light nearly as well as it perceives green. So don't be fooled. It doesn't mean that it's mostly oxygen. It's actually mostly hydrogen, but it's got enough oxygen to give you that teal colored glow.
Cool. All right. So the next one on the list is not far from here. It's off of Alberio, and we might want to stop at Alberio and use that to sync, and then it will be a quick hop over to the next target.
Good place to stop.
And I think we have some Cal students on looking in tonight. So this is the Cal stars, and you'll see why in just a minute here.
And while we're moving over there, Tracy asks, are we actually seeing what the true color of the star, teal? Yes, it's the true color, but it's not the star, it's the nebula.
The surrounding gas. Yeah.
Yeah. I don't know if you can see it in live view or not.
Oh, yeah. Let me get over to live view here. Sorry. I was busy looking at the comments. Okay, there's Alberio. Let's get that more or less centered.
All right.
I guess we'll want that. If you can,
now I want, especially if there are any Cal students on here or Cal alumni.
Yes,
I want you to notice
the colors.
The colors, blue and gold. And those colors are actually indicative of the temperature of the stars. A blue star is a very hot star. A gold star is a much cooler star. In the real world, hot is blue and cool is red. So when we look at stars, we can tell their temperature by looking at their colors. And we can be even more precise by measuring the actual intensity of the light from the star across the whole spectrum. And the wavelength at which the maximum intensity occurs, we take that wavelength and we can do a rather simple calculation to determine the temperature of the star. But blue is hot and yellow or orange or red, those are cool stars. Now, the orange star looks a lot brighter, or the gold star, I guess I should say, since we're talking to Cal students here. The gold star looks a lot brighter, and that may fool you into thinking that it's the closer of the two stars, but it turns out that it's not brighter because it's closer, it's brighter because it's bigger. The white star, the blue star is in its main sequence. The gold star has started to approach the end of its life and it has swelled up. And when the star swells up, it has more surface area to radiate light. So even though its temperature is cooler, it appears brighter because it's got more surface area radiating light. And it is physically slightly farther away from us than the blue star. Okay, so I think we're synchronized on this.
Great. So let's try going to this other object.
All right, hang on here. Let me
got it in there.
Key it in.
So what we're going to try to look at, I've only seen it in the 60-inch telescope at Mount Wilson, and may have seen it in the 100-inch there as well. It's called Campbell's hydrogen star, and it's another planetary nebula. What's interesting about it is that it's very red. It's one of the only discovered planetary nebulas that is like mostly a deep red color, and it was discovered by William Campbell at the Lick Observatory many decades ago. I think I have the date on that sheet. I think it was in the 30s. Is that the right?
Let's see. You say.
Did say something there, and I don't even remember what I said.
1893.
Oh, okay. So it's even earlier than I thought.
Yeah. All right. Well, we should be there.
Okay. We'll go back and try to. This is still 6826 here. I'm going to go for the same exposure. Why not? Let's see what happens. Because it's roughly the same brightness.
Yeah. In fact, according to this, it's exactly the same brightness. So.
Yeah, so it should work. And we'll see if we see a color difference. Well, first we'll see if we see it. Speaking of Mount Wilson, maybe some of you were following the fires in Southern California, and Mount Wilson came very close to losing its observatories. And the fire crews were phenomenal. They lit a backfire at the last moment that stopped it, and the entire facility has been saved.
Yeah.
So
They have a couple of cameras up there that you can, webcams that you can view. And it was scary
Oh, look at that.
to see actual flame
Oh, there we go.
just beyond the dome of the observatories.
There we go. All right, so you can see that this is much redder than anything else around here. You can see a red star here. You can see some blue stars here, but this is very distinct. And it is a planetary nebula, just like 6826 was. But due to the different composition of gas, it has a very different color. So these are fun to find through a telescope because they all look completely different from one another. And they have a lot of interesting structures and color associated with them.
Yeah, we see planetary nebulas that look like hourglasses, like butterflies, like donuts, just all kinds of different shapes.
Cat's eyes.
Cat's eyes. Yeah.
Had to mention that for Kathy.
Yep, that's right.
Yeah.
Well, this is good. This is much better than I thought.
So a clown face.
With even more magnification, we would be lucky to maybe see that. You could actually see it here, that the very center, I don't know if those of you at home can see it, the very center is dimmer than the surrounding area. And that's not an artifact. That is quite real. And through an even larger scope, you could see that naked eye.
All right.
Great. Well, those are the two objects I had. Is there anything
All
else
right.
you want to put it on?
No, I can't think of anything off the top of my head.
You know, Mars is up there almost high enough. I'm not sure if it's quite there yet.
Is it more than 15 degrees above the horizon?
It looks like it's right about that, maybe a little more. So it might go.
Wow.
I'll tell you what. Why don't we give it a try?
Let's try it out.
I gotta move things over and sync on alpha.
That's kind of a different direction than I'm used to seeing. So I'm going to watch the cabling while we do this. I'll put it on live view.
Okay, I'm gonna go in a couple of steps here. So Mars is in the eastern sky.
Very obvious right now too. It's
low near the.
That's not Mars that you're seeing.
Yeah. We're just looking at.
There's the bullseye.
Oop.
Overshot.
Too much.
Overshot the bullseye.
All right. We're closer. Well, I'll tell you what. Let me just key in Mars here and we'll see what happens.
Yep.
It might say no. I think
Might
that looks
say
like it's
beyond
up.
the limit. It's really right on the edge.
Looks to me like it's up high enough. I don't know.
Let's see what it says when I try to slew to it. Well, says we can do it.
Great.
Here we go.
Make sure the cables don't get tangled.
Oh yeah, it's 16 degrees above the horizon.
Yeah, 1 degree
higher.
All right. Well, there it is.
Oh,
Get it
There it
centered.
was.
Then I'll adjust the exposure, and we may take actual camera shots.
But this is a
trying to get more
five.
detail.
This is a 5-planet night.
yeah. That's pretty rare.
Of course, I'm counting Pluto as a planet because it is a dwarf planet. And in my book, a dwarf planet is still a planet. I know. I'll get in trouble for saying that, right?
We'll let it go.
Yeah. We'll just refer them to your book.
Yeah.
All right.
Neil deGrasse Tyson will be phoning me tomorrow morning.
Right.
Complaining.
Yeah.
Yeah. Hey, you
All
know,
right, that's pretty good right there.
he's in New York. He can't hurt you.
Yeah.
All right, let's get this to.
I want to see
All right,
details.
very nice. Then get some detail.
Oh, there you
Oh,
go.
that's
Hey, look
pretty
at that.
good.
Look at that.
Polar
Yeah.
ice cap there.
Yep.
Good.
Yeah, that's pretty good.
Yeah.
All right, so the polar ice cap is at about 7 o'clock, right? That's the more obvious one anyway. And you see that's kind of like a whitish dot that is brighter than everything else around it. That's carbon dioxide ice.
Yeah. So you see some dark features sort of at the lower half of the planet. And the planet is slightly tilted. So the lower third, I guess you'd say, is a little bit darker. That's because that's an older region of Mars, and it's a much more rocky, a lot more craters there. Whereas the lighter region that you see up above, that is a much newer region. It's covered from the volcanoes on Mars, which are all extinct now, but you get a lot. Well, you get even better there. That
Yep.
Yeah. So the volcanoes are spewing stuff out and it's scattering dust all over the place, and so it's a much sandier region with fewer craters, smoother areas, and a lot of that is actually lower in elevation. So we think at one time Mars had some shallow seas on it. And so if you were to see a image of Mars taken from, say, 3.5 billion years ago, you might see oceans in that part of the planet. But it's all dry now. All the water is either in the ice caps or underground. Right?
This is great.
Yeah.
We
Yeah.
have a question. What season is Mars in right now? Well, we can see multiple seasons on Mars because we can see the poles.
Yeah, I'd have to look it up. And Mars is just like Earth, in that one pole has a summer while the other side has a winter.
Yep.
It looks like the southern pole is tilted a little bit more toward us. Am I seeing it that way? In which case,
I'm guessing the side where we see the pole is in summer.
yeah. So that would be the summer side, and the other side.
And I'll tell you, so it's only a it's like a balmy 70 degrees below zero.
Yeah. Right.
It's summer. Yeah, it's not a comfortable place, folks. I mean,
Yeah. Mars is only about half the diameter of the Earth, but like the Earth, it's tilted. Its axis of rotation is tilted relative to the plane of its orbit. So Earth's axis tilt is about 23.5 degrees. Mars's tilt is about 25 degrees. So very similar tilt, but we see evidence that the tilt of Mars has changed over time quite a bit. And the reason Earth's tilt has not changed nearly as much is because Earth has that big moon orbiting around it. And it actually helps to stabilize the tilt of our rotation axis. Whereas Mars, although it has a couple of moons, they're very small. They don't affect the planet very much. And so Mars can tilt more or less than what it is right now.
There's an interesting question from Jasper. Are we sure all of Mars's volcanoes are extinct? How do we know that?
Well, we don't see any activity.
Yeah.
And we do have spacecraft or on the ground at Mars, and we don't detect a lot of volcanic activity. There are some, but not a lot. You may recall a couple of years ago, the InSight spacecraft that landed on Mars. It has a seismometer that has been recording Mars quakes, if you will. And there just isn't much sign that there's any more significant volcanic activity going on there. But we know at one time there was a lot because we still see the old volcanoes. In fact, the highest mountain in the solar system is Olympus Mons on Mars. And to give you an idea how big Olympus Mons is, its height is 3 times the height of Mount Everest. Its base is the size of the state of Arizona. So it's a big mountain.
So if you walked it and climbed up to the peak, it would just be a very gentle slope.
Right, right. But
It would
it's
just
really
keep going.
It's really
Right.
high.
Yeah.
So
I want to try something real quick, if you don't mind.
okay,
I
okay.
think it's worth a try. I want to see what some stills look like here. And there's Campbell's hydrogen again. I'm going to put it back on 800.
Yeah, this is what you do when you're trying to photograph planets: is you fiddle around with different exposures and different ISO settings and exposure times and so on, trying to find the optimum. And one technique that a lot of astronomers use, especially amateur astronomers, is they put a video camera on their telescope.
Oh, that blew it out. Never mind. Let me go. Let me go to where I want to go here.
It blew up.
Yeah, it blew up. That's what Mars looks like when it explodes. Yeah, that's not what I wanted to do.
Yeah. So anyway, what they would do is they would put a video camera on the telescope and just shoot video for a couple of minutes, and you end up with hundreds of individual frames. And in each frame, the planet is very faint.
Okay.
And what you do is you go through and you look at all of the frames and you pick out the ones where it's sharpest. Because of atmospheric distortion, the image is constantly going in and out of focus, and you find the ones that are the sharpest, and then you stack them electronically. And as you stack them, you get rid of more and more of the noise, things sharpen up a lot more, and they become brighter. And eventually you have a really high resolution image of Mars. There's a guy in England, his name is Damien Peach, and he is a master at doing this. He's an amateur astronomer. In fact, he has a telescope the same size as my backyard telescope, and I'm always amazed at how much more he can do with his telescope than I can with mine. But he's just really good at doing this, and he produces at every Mars apparition. Mars shows up in our sky every 2 years and 2 months roughly, and each time he does this with Mars, and he produces he collects enough images to produce a short movie that shows the complete rotation of Mars. And it's just really amazing how much detail he's able to capture when he does that.
Getting to where I want to be. It's getting close here. There we go. Okay, so now I'll bump up the magnification a little bit and take a few more. See if I could catch a sweet spot here. 200, 250. Let's start. Oh, that was blurry. See, so we do this until we find a moment of nice seeing, and you can see I caught it right during a maximum blur. Okay, that one wasn't too bad. So basically, try to luck out. But if I was taking video, I'd have 60 frames a second, and I'd be able to pour through them. Actually, that one is pretty decent. Get a lot of the. I'm going to actually take this down to 400th of a second. Try to beat the seeing here with a faster exposure. Okay. I can go even more. Go to 800th of a second and bring the ISO up. Yeah, that's not too bad.
Yep.
All right, well, that's what I wanted to try. There we
All
go.
right. Well, I'll tell you what, if you'll let me share my screen again, assuming you can figure out how to do it. So you're going to have to unshare there. All right. I mentioned, can you see that?
Yeah.
Yeah.
All right. All
Yeah,
right.
beautiful picture.
Watch this.
Wow.
This was
Is
taken.
it?
This
Is
was
this
taken.
Damien's?
This is Damien Peach. This was
Yep.
done with an 11-inch Schmidt-Cassegrain telescope in his backyard.
That's amazing.
And
I remember
again,
when he did this. I
well,
think
he actually does it every 2 years or 2.5 years, roughly. So-
my reaction is always, why do I bother?
I know.
Yeah.
Now the image is inverted. So
Stop there.
Up.
You go back, drag that back so you can look at Olympus Mons. I think that's Olympus Mons, isn't it?
Yeah, right there. Right there. That's it right there.
Yeah.
Yep. So anyway, this is what a lot of patience and a lot of image processing can do for you with a amateur telescope. So
Jose is asking, is that RASA? I don't know what that term is. Do either of you guys know?
no, not off the top of my head.
Yeah, Jose, if you could tell us what RASA means, maybe we can answer.
Most of the time we can make up an answer, but not for this one.
Yeah, for
No, it's all
those
caps, RASA.
Yeah, for those of you who like this kind of thing, all you have to do is Google Damien Peach.
Yeah,
Exactly like it sounds, and you'll find some amazing stuff on the internet.
Yeah, he has a bunch of these. He, like I say, he does this every 2 years, 2 months, whatever the cycle is between Mars apparitions, because of the rate at which the Earth orbits the Sun versus Mars. Mars comes to what we call opposition every 2 years and 2 months. So this year, Mars will be at opposition on October 13th. And that's the point when Mars is directly opposite the Earth from the Sun. So the Sun will be on one side of the Earth and Mars will be at exactly the opposite side.
Thank you, Kathy. She posted the link. For those of you who are interested, the link to Damien's website just came up.
Yeah. Now there's another guy, what's his name?
Christopher Go.
Christopher Go, right. He does this kind of stuff also. And I believe he's in Indonesia or the Philippines, something like that.
Yeah.
And
Southeast Asia.
Yeah. And these are just guys, they have moderately good observatory equipment, telescopes, and a lot of patience and a lot of skill at doing this kind of thing. Much more so than any of us here. So, all right.
All right.
Okay. Well,
I think we had a pretty good night here.
Yeah.
Well, looks like people enjoyed it.
5-planet night. Okay. Well, a couple of things I want to make sure you're aware of. Fall is coming up. I believe it's on Tuesday at 6:30 in the morning is when fall starts. And next week, we are going to be doing a special program. We actually are going to be doing 2 programs on Saturday night. At 7 o'clock, you're going to hear a lecture from somebody from the Lawrence Livermore National Lab talking about lunar landing sites, because next Saturday is International Observe the Moon Night. And so we are going to do that program at 7 o'clock, and then at 9 o'clock, we're going to do our program, and we are going to be pointing the telescope at the moon, assuming the weather cooperates, and doing a little tour of the moon with our telescope here. So
Yeah, it'll be all moon on
all
next Saturday.
moon, yeah.
Yeah.
You want to make sure to check that out, and always check Chabot's webpage. Click on that donation button, help us out, because we are right now closed to the public. We're getting ready for our grand reopening next year, and we need your continued support so we can get there and be successful. So with that, good night, everybody. Have a
Good
good
night,
evening.
everyone.
Good night, all.
Thanks all for joining us.